This is Bill Farmer again. Welcome back to Software Engineering 2FA3, Discrete Math and Applications 2. Last time we had discussed two theorems, Theorem 4 and Theorem 5, that show that regular expressions match the same languages as finite automata, both non-deterministic and deterministic except. So we're going to prove today Theorem 4. So Theorem 4 says that if we have a regular expression that matches some language L, then there's going to be an NFA with E transitions that accepts the same language L. So this proof is a proof by structural induction. Now, why do we use structural induction? Well, let me remind you that regular expressions are defined, we define regular expressions as an inductive set. It's an inductive set defined by these six constructors. And the first three constructors basically define the base cases, and the other constructors show that this inductive set is recursive. So regular expressions are defined as an inductive set. So if we're going to prove something about regular expressions, we can prove that using structural induction. And that's what we're going to do. So I want to mention before we get started that this proof is named and due to a person named Ken Thompson. Now, Ken Thompson's actually a pretty famous person. He is a Turing Award winner. He's the developer of the Unix operating system. He's also the inventor of the B programming language, which was a precursor to the C programming language, which is still used today. And another thing to say about him is he worked at the old Bell Labs. This was the research laboratory that was run by AT&T. AT&T at the time had a monopoly in the telephone system in the US, so they had a very large amount of money that they could devote to research, and this was research at Bell Labs, which is one of the most famous research institutions in the history of the United States. Okay, so what we're going to do, instead of proving Theorem 4, we're going to prove a stronger theorem. And the stronger theorem is that let alpha be a regular expression and it matches the language L. Then there's going to be an NFA n sub alpha with E transitions that accepts L, but this NFA is going to have certain properties. It's only going to have one start state and one final state, and there's going to be at most two transitions from each state. And there's going to be no transitions from the final state. So we can represent this n sub alpha graphically as this box. So this is the start, and this is the final. And inside there's a bunch of states, but there's only one start state, there's only one final state, and there's nothing coming out of the final state. Okay, so we're going to prove this by structural induction. So our proof breaks down into 6 cases corresponding to the 6 constructors for regular expressions. And we're going to prove this statement for each of these cases. So the first case, which is a base case, is what happens if alpha is the empty set symbol. Well, then this will be our NFA with epsilon transitions. We'll have a start state and a final state, and there will be no connection, and that means that we won't accept anything with this. In other words, the language we'll accept will be the empty set language, which is exactly what we want to accept. Now, if alpha is epsilon, we'll have a single state. Q0 will be both the start state and the final state. And the only thing we can accept, the only language we'll accept here, will be the set of the empty set symbol. And again, that's exactly what we want to accept, because the empty set symbol matches exactly this language. Okay, for the third base case, alpha is going to be a member of sigma, our alphabet sigma. In this case, this will be our NFA with epsilon transitions. We have a start state and a final state, and the only thing we're going to be able to accept is A. That's it, but that's what we want to accept, because the only thing that matches A is this language. Okay, so these are the three base cases. They're pretty simple. And now we're going to have three induction step cases. So the first one is alpha equals beta plus gamma. So because we're using structural induction, we can assume that we can already construct n sub beta and n sub gamma. And these NFAs with epsilon transitions, they're going to satisfy the conditions of the theorem, and they're going to accept these two languages respectively. So here they are. Here they are in the two boxes. And what we're going to do is we're going to create this finite automata by creating a start state, having epsilon transitions to both of these, and then creating a final state and have epsilon transitions to both of these. And we can see that all the conditions are satisfied. We have at most two transitions coming from any node, and we have no transitions from the final state. And it's pretty clear that this is going to be true. Well, we know this is true. And we know that L for this, it's going to be, there's two possibilities. We can accept the things in this language. So this is going to be, or it's going to be, we'll accept the things in the language we get for this. So this works. So this shows how, if we already have n sub beta, n sub gamma, how we construct n sub alpha. So the next one is if we have alpha equals beta gamma. Again, we're assuming we already have these two, and they accept these two languages. And we need an NA such that this language of, I should say n alpha, so that the language of n alpha equals the concatenation of the language of n beta and the language of n gamma. And this NFA with epsilon transitions works. We take the n beta and the n gamma, we connect them with an epsilon transition, we make this the start state, we make this the final state. And if we have something in here, it's going to look like xy. This part will accept the xy, then we'll have an epsilon transition, and this part will accept the y. So this works. And our final case is when we have alpha equals beta star with the asterisks. And so in this case, what we need, again, we are going to assume that this works, and the language of n sub alpha, that's going to be the language of n sub beta where we apply the asterisk operation to it. And so when you apply the asterisk operation, that means we take all the we concatenate all the strings in here as many times as we want, and it also includes the empty string. So we start with this, and then we can get concatenate members of this by just going around and around through this. And then we also need to have the empty string, so that's why we have this. So this will be the start state. If we go this way, we will get a bunch of members of this language being concatenated with themselves. And if we want no members, or we just want the empty string, we go this way. Okay, so that completes the proof of Theorem 4. It's a very good example of how you use structural induction. It's also a good example of how epsilon transitions allow us to build more complex finite automata from simpler finite automata. Okay, so on this slide, I'm just going to list some closure properties of regular languages. So there's 5 of these listed. We already know the first 3. If we have 2 languages that are regular, their union will be regular. Their concatenation will be regular. And if we apply the asterisk operator, that will be regular. But we also have 2 other closure properties. If we have a language that's regular and it's a sublanguage of all the strings over alphabet sigma, then we know that the complement of that language is also regular. And we also know that if we have 2 regular languages, their intersection is regular. So the final thing we're going to talk about in this section are some applications and topics. So what this technology that we've looked at, regular expressions, DFAs, NFAs, this technology is actually very useful. And so I'm going to give 2 of the most important applications. The first is lexical analyzers. The second will be dealing with text editing. So when you're going to write a compiler to take a program and to produce machine code that you can execute to run that program, the first thing you need to do is take the program, which is going to be a big sequence, a long sequence of characters, and turn it into a sequence of tokens. So as I say here, a token is a string that represents meaningful symbols. So you can think of strings in a programming, or tokens in a programming language, they're like words in a natural language. So they're sets of symbols that are characters that are meaningful. We can think of our program, once we tokenize it, it's now a sequence of tokens. So how is this done? Well, a token analyzer is going to be part of our compiler. You're going to take the program, you run the token analyzer, it's going to convert that string of characters into a string of tokens. And the token analyzer is going to work as follows. The set of tokens is going to be defined by a regular expression. So we're going to have a regular expression alpha, and it's going to match that set of tokens for our programming language. And then using just what we saw, we can take alpha. So we start with alpha, and we can construct an NFA with epsilon transitions that's equivalent. And then we know we can take that FA with epsilon transitions, we can produce an NFA without epsilon transitions. We talked about that previously. And then using the subset construction, we can produce a DFA. And then we can use an algorithm that can produce a minimum state DFA that's equivalent to that. So we start with a regular expression, and we end up with a minimum state DFA, and that will be the core of our lexical analyzer. That will be used to identify the tokens. Okay, so that's the first application. The second application is, suppose we wanted to take a text file and search for a string or a set of strings that have a certain pattern. Well, we can write that pattern, express that pattern as a regular expression. So we can write a regular expression that represents the set of strings that we want to match, and then that regular expression we can convert into an NFA with epsilon transitions, and then we can directly simulate that NFA with epsilon transitions to find all the instances of the string in this piece of text. And once we find these instances, we can either note where they are, or we can also do replacement. We can replace them all with other strings. Now notice here we ended up with a minimum state DFA. Here we are simulating the NFA with epsilon transitions. The difference here is that when you're doing a string search, you want to do that fast, and you don't want to spend the time of creating something that's more involved, the minimum state DFA. But when you're doing lexical analyzer, you're going to be processing the whole program. So you want to run as fast as you can, and you're willing to invest time to produce the thing that's going to allow you to go faster the time. So the first approach, where we started with a regular expression, we invested time to produce something that will work fast. The second approach, we wanted things to work fast right away. We didn't want to wait for the investment of creating this minimum state DFA. So we directly simulated the NFA with epsilon transitions. Okay, so there's a number of topics we did not cover concerning finite automata and regular languages. We mentioned before that there is a simple algorithm that will collapse a DFA into a minimum state DFA that's equivalent to it. There's also a lemma called the pumping lemma that is used to identify non-regular languages. This is an important part of the theory we did not look at. Another thing is the Myhill-Nerode theorem. This theorem shows that a language is regular if and only if a certain relation has a finite number of equivalence classes. So you can use this theorem to show that languages are regular. And we also have not talked about other finite automata with output. So there's two kinds, Moore machines and Mealy machines. Moore machines produce output depending on what state you're in, and Mealy machines produce output depending what state and what symbol you're processing. And finally, there's also two-way finite automata. These are automata where you can go back and revisit symbols that you've already looked at. So these are topics that some of you may want to look at in some depth. They're interesting topics, but we've decided that we would not look at them for this set of lectures. Okay, thank you very much. We will be starting a new topic next time.